Thank you very much for the introduction and for the opportunity to present here at this wonderful workshop. And it's a congratulations on this neat idea to reflect on the centenary, in particular of Frank Knight's publication. Don't expect too much, but let's say I think has been a long afternoon, and so my talk again will be a slightly different style than the one you've seen before, but maybe that's good at this stage. So I took the conference as an incentive to read Frank Knight again, really. And of course, I'm not a historian, so I don't try to understand what exactly he meant, but I try to take it as an inspiration for us, yeah, so and for our work, and how the things that you can find in this really deep book, I have to say, are reflected in our current research. So I will start with Frank Knight, or I interpret him a little bit, and then talk about insurance. So three papers actually that are related to what I was doing in the last years. So insurance premium, then I will turn to equilibrium and absence of arbitrage in financial markets. And last but not least, I want to speak about an idea that is related to Frank Knight's idea, namely market breakdown under uncertain prices. So not uncertainty averse preferences, but uncertain prices. And then there will be a short outlook. So let's get started. So if you read Frank Knight, then it's an interesting title. No, risk and uncertainty belong together. But if you think risk, uncertainty, and profit, in what sense? Well, Frank Knight is considering a classical question in economics, in German Unternehmerlohn, yeah, the emergence of profit under conditions of competition. Because if you write down a very simple model, general equilibrium model, let's say, we would say nowadays, and Frank Knight really describes it actually in a very mathematical way, although he doesn't use any formula at all, yeah. But he describes very nicely that profits are zero in competitive markets, of course, when you know everything, you know, in particular in terms of positively homogeneous technologies. In his own words, the quotations you can only always find in this sort of blue-green color, the spirit of the Chicago River, maybe, yeah. So in ideal exchange, the quantities that are exchanged are equal in value terms. And there's no chance for anything like profit to arise. And really, if you read like value terms and so on, he's also thinking in marginal terms already. So at least in marginal terms, there's no positive profit if you are in a deterministic setting. And then he goes on and says, okay, now you can say maybe under risk, yeah, then there's positive profit, you add risk aversion in modern terms and so on. But then he says, no, this is not true. Yeah? In an environment where there's risk, so when you know the probabilities perfectly, then profit should actually disappear again. And sort of the story is there's proper uncertainty, and this explains the existence of profit. And I will come back to this at the end when we know more about what's currently going on. So actually the first chapters of Frank Knight's book are like a textbook on microeconomics, no? in my own reading. And it was used as a textbook, I understood from these nice lectures yesterday. And then in chapter 7, he continues with uncertainty. So he says that utility and profit maximization applies in small worlds when everything is perfectly known. A little bit in spirit like savage small worlds. Yeah? But, and then he explains why risk is not a problem for markets, particularly if you think of modern insurance and so on. The bursting of bottles, so he's talking about a champagne producer. The bursting of bottles does not introduce any uncertainty or hazard into the business of producing champagne. Now, why not? Because it's very difficult to predict when a single bottle bursts, but we don't care. Yeah? So each single bottle bursts at random, but by the law of large numbers, which is very specific in the case if you have no uncertainty. You've seen, in the case of uncertainty, you've seen Xi Jinping's talk, there's a little bit more vague, let's say, the law of large numbers. The total number of burst bottles is known, and then it's like a fixed cost for the firm. No, you know that on average 3 bottles burst per month. You take it as a cost, then it's like it's again deterministic. So markets can perfectly price such randomness, But then he continues and saying, but this mathematical type of probability is practically never met with in business. And that creates then a problem, of course, no? That we can deal with only lately, in my opinion. So in typical business situations, there's no law of large numbers that allows to estimate the probability of success with accuracy. Maybe with a certain range, no, as we've seen in Chile's talk. So then the famous chapter 8, which is more vague, admittedly, because I think here in this chapter, Frank Knight himself is exploring certain ideas without knowing exactly how to pin them down. Yeah? So uncertainty explains excess profit. So there's a famous distinction between measurable uncertainty and unmeasurable uncertainty, risk and uncertainty. And then there's this quotation that I like, the income of an entrepreneur is larger than zero, as there's a scarcity of self-confidence. So I sort of like this. Yeah? I'm not sure, if you look at politicians, maybe sometimes you ask yourself if there's really a scarcity of self-confidence. But you see what you need as a successful entrepreneur. This is a combination of scarcity of self-confidence combined with the power to make guarantees to employees. So what an entrepreneur does is he gives a fixed wage, so an insurance in some sense to his workers, and he has the confidence to attack uncertainty. So excess profit then is the result of confronting uninsurable uncertainty. So these are interesting ideas that also sort of inspire my own research and let's say the work of the last 30 years or so, also starting with people like Jacques Glibor, whom we have seen yesterday, and then of course on the technical side, Xi Peng, we are now able to talk about such things, even in mathematical economics. Before I start with the more, let's say, concrete stuff, let me show you a taxonomy of uncertainty that I like. It's taken from a paper by Loh and Müller in 2010, which I like a lot. So the world one, so I'm going to call these things always world. World one is the world of physics in the Newton sense. So everything is governed by differential equations. There's no uncertainty, no risk. Past and future are perfectly known. Of course, this is for economics. It's just a benchmark model, but of course not what describes the real world. Then there's risk, objective probabilities. So that's classical probability theory in the sense of Kolmogorov. Then there's the next world, which is closer to reality, I would say. And that's the world of statistics. Yeah? So and let's say that's the world of statistics when statistics works well. And they call it fully reducible uncertainty. So we do have Knightian uncertainty in the sense that we don't know the probabilities, but let's say we can reduce it to a parametric case. Yeah? We don't know some parameters and we can estimate those parameters because in the background there's something like a law of large numbers or some stationarity, ergodicity, and so on. So in that case, statistics reduces uncertainty to risk and everything is fine. That's a Bayesian world, kind of say. So Bayesian world maybe, or even frequentist statistics works here. And then the world that we are talking about and that we are able to deal with is the world of imprecise probabilistic information, using here a term that has been coined by Jean-Marc Talon, among others, which I like. Yeah? So here we do have irreducible uncertainty in the sense also, in the technical sense that you've seen in the previous three talks, so in particular by Shige and by Francesca. So and then you are left with a whole cloud of probabilities, for example. Yeah? So and maybe one day we are able to go one world above, but maybe that's after our death. So let's stick with world 4 here, for this talk. Good. So that's my let's say reference to Frank Knight, and now I would like to talk a little bit about some papers that are related to these ideas that I've been working on in the last couple of years. So let me start with an axiomatic piece on insurance, Premia. That is joint work with Max Nendel and Maren Schmeck, who are both at Bielefeld University. And here, so let me give you the idea. So the idea, of course, premium principles are fundamental in the field of actuarial mathematics. They give a foundation of how and why premium principles are justified for insurance companies. Classically, of course, if you look at textbooks in insurance, a premium principle is always a function of the probability distribution of losses. In particular, you assume that you know the probabilities. Yeah? So you're in world 2, technically speaking. Maybe then you can say in world 3 everything is okay because we can estimate everything. So just to say that all these things are not just arcane academics, what we're doing here. No? So the problem of Knightian uncertainty, which is also sometimes called model uncertainty in insurance, is by now widely recognized, and in particular in Europe, for the regulation, Solvency II. This is a thing that insurance companies need to deal with. So this is a topic that is at the forefront of research, but also at the forefront of practical applications of our theories. Just to show you that typically in insurance, of course, we were used to assume that the probabilities are known. I have a classic here from Hans Bühlmann from the ATH, Eidgenössische Technische Hochschule in Zurich. So you see immediately, he wants to talk about premium calculation principles, and he starts with a distribution function. And then it goes on. Okay, so how do insurance premia typically work? You know that the basic ad hoc approach is to look at the expectation, or if you know the probability, you just compute the expected loss. And then if you have some market power as an insurance company, you take some safety loading, for example, something like this. So the premium would be expected loss plus some parameter theta, the variance of the losses. And just to give you immediately what we do, so we show in a more general setting under Knightian uncertainty, we also get an additive decomposition, but the risk measure is, expectation is replaced by a risk measure. You know that, at least the experts in finance know that the expectation is a simple form of a risk measure, and the variance is replaced by what is called a deviation measure. So in that sense, we generalize this basic decomposition and have some applications that are also related to finance and to other topics in this conference. So let me give you now the formal setup. So here you see we always consider a measurable space, just to stress it. There's no P, so that's the Knightian uncertainty part, and we don't start with a probabilistic setup. Then for this talk today can be generalized. Let us take the space of all bounded measurable functions. And then the market is given by a set C. So think of a convex set or maybe even a subspace or so. These are all the insurance claims that we want to price or that are priced by the market, and that we want the premium we want to characterize. For technical reasons, normally X is thought of as a loss and X is greater or equal to 0, but we want to be able to shift by amounts of cash. So we assume that if you add cash here, and cash can be negative, then you are still in C. It's just so let's say we close the set of contracts by this operation. So, and what is a premium principle? Generalizing what Bühlmann has done, we say that a map is a premium principle if it satisfies these two simple conditions that make a lot of sense, also from an insurance point of view. So first of all, this is cash additivity, or cash invariance. So if I have a loss X, and there's I add a certain amount of money to it that is known. So I know that tomorrow I have to pay the additional 100 euro. Then this should be immediately taken out, And okay, typically I will discount by an interest rate, but here for simplicity we assume that the interest rate is 0. And then this deterministic part, this known part, of course, there is no problem with it, yeah, to price it, and we should give it a fair price, otherwise it would be arbitrage. Then the second condition is, okay, if I have nothing to insure, then this is just normalization, if you like, the insurance premium of 0 is 0. And of course, if I have a real loss, so x is greater or equal to 0, then if I don't want to go bankrupt, yeah, then I should take a positive premium for it. So these two things really have a meaning also in insurance terms. Yeah. So the first one corresponds to no unjustified risk loading. You can't take a risk loading for things that are deterministic. So in particular, h of m is m. And the second one is no bankruptcy. No? So there's minimal conditions on premium principle. And here comes, I have to, sorry, before I state the theorem, I have to tell you what a risk measure and deviation measure are. Can be quick here, I think. Risk measure, that's a different sign, yeah. Here, sign convention, so that it's a little bit puzzling maybe, but the risk is typically in risk, X is typically a payoff, not a loss. So that's why we have a different sign convention here. If you add money to a position, then the risk is reduced by this known cash amount. Okay. I think that's clear. And the risk measure is also monotone, but in the other direction now. Yeah. So if x is always pointwise greater equal to y, then the risk of x is lesser equal than the risk of y. And typical examples are the expected loss. Yeah. So now here's I have this minus again. Yes, as you know, there's a sign thing. Or I can take in the spirit of, let's say, in preferences, it would correspond to the Walsh-Mitre or maximal loss. No, so you can just look at this maximal loss. It's also a risk measure, and these are the two extreme risk measures in a certain sense. What is a deviation measure? A deviation measure is a mapping D that generalizes the variance. In particular, for the variance, you know, if you add a number m, then the variance doesn't change, and the variance of 0 is 0, of course. And the variance should always be non-negative. Yeah? The deviation measure should always be non-negative. Good. So if you take the two things together, then you get the theorem here. So a mapping, this H is a premium principle if and only if it can be decomposed into a risk measure plus a deviation measure. It's easy to check that if you have the two things here, risk measure and deviation measure, then you have a premium principle. The other direction might be less obvious. And in particular, also the decomposition need not be unique. But we have a certain maximal decomposition, which also gives you immediately a way how to prove the other direction here of this theorem. And it's the following one. It's in the spirit of super hedging in finance. Yeah? Let us define the following object here. So H is a premium principle. And then I look at this, for given loss X, I look at insurance contracts that help me to stay on the safe side. Yeah? X0 plus X is greater equal to 0. So I cover all my losses. No? X0 greater equal minus X. And I try to find the cheapest insurance contract that covers me fully. So for those of you who are in finance, you know that this means that this is like super hedging. Then, okay, I want to just define d min as the remainder of what we have here. And then we get that R max is a risk measure, d min is a deviation measure. So we do have the decomposition that we want to have. And this decomposition is in a certain sense unique. In the sense that every other decomposition which of a premium principle into a risk measure and a deviation measure is such that the risk measure is dominated by the R max, and the deviation measure dominates the d min. So in that sense, this is a sort of minimal maximal unique decomposition. Good. I skip, in the interest of time, I skip a little bit the intuition, but I've said this before, yeah, so this R max can be written exactly in the spirit of a superhedging functional, and therefore it's easy to see that it's a risk measure. Just to show you that the decomposition is not unique, if you, and this is related to some interesting work by my Italian friends from Milano, Maccaroni et al., no? Who have worked on also on insurance markets under Knightian uncertainty. If you start with the variance principle and you apply this procedure, then the R max actually is not given by the expectation here, or expected loss, yeah? But it is related to something that is related also to mean variance preferences under Knightian uncertainty, namely the Gini index. I don't have time to go into detail, but just to show you that they are in the paper, then we are going to deal with some other interesting stuff that I don't have time to cover here today. No? For example, the ambiguity indices that were introduced by Castagnoli et al. Are also covered here. But now I would like to come to another topic. So namely absence of arbitrage and equilibrium in financial markets under Knightian uncertainty. And this, to this end, I would like to recall a little bit again the history of economics, since the workshop is a little bit in that spirit. So the later Nobel laureate Eugene Farmer stated in 1970 the famous efficient market hypothesis. If financial markets are informationally efficient, then the expected returns of all assets are equal. So one way of interpreting this statement is to say that there's a real world probability, P. It's commonly known, yeah, so public info, common knowledge. And the rate of return of an asset, gross rate of return in expectation, is equal to 1 plus R, where R is the risk-free interest rate for this corresponding maturity. Now, as such, of course, we know it's not true, no, because typically assets have a higher expected return than the safe return, but it's a starting point, let's say. No? So, and then immediately, let's say you can go to risk aversion. So you stick with the risk, but in a world with risk aversion, if you look at an expected utility maximizer with a concave Bernoulli utility function, then the first order condition entails that you have to adjust here by the marginal utilities. Now, that's what Frank Knight means when he says adjusted in, for value terms. No? So here's the value, the marginal value. So the expected return discounted properly with U prime is equal to the safe return, no? And this is a constant that you can bring on the other side. No? So to make this a probability density. And then, so if I introduce this probability density Q, if I use this U prime here as a density, normalized with this constant, then I get my efficient market hypothesis under the so-called risk-adjusted measure Q in this form. So expected returns under Q are all the same for every asset. And this Q is, of course, corresponds now to the famous equivalent Martingale measure in finance. No? In finance, later, yeah, so it took us a long time somehow to realize this. But let's say it started with Creps, in my opinion. That's a fundamental theorem of asset pricing. You don't need any utility functions, anything. All you need is you require that the market is efficient in the sense that there's no arbitrage. And then you get a measure Q that is equivalent to the original measure P that you started with, such that you have this famous equation. And Q and P are sort of related because they have to be equivalent. That's important in the following, because null sets under Knightian uncertainty, of course, it's a subtle issue. For example, for the G expectations, the whole theory has been developed in order to be able to deal with sets of probability measures that are not dominated by a single probability. So the null sets can be very different for different P's and Q's. So now I would like to speak about viability and arbitrage in world number 4, as I call it today. So this is based on joint work with Matteo Bozzoni, who was in Oxford, by the way, for a while. Now he's back in Milano, and Metesona was in Princeton. The paper was recently accepted in Econometrica. So what we try to do is here, and there's a large literature on that, but we look at it from the economic point of view, let's say, asset pricing without probabilities. So this language is sort of no longer in the paper because there was a discussion how to call these things there, but I would like, that's why I've written it in small print now, but still like sort of like the wording. So what we do, we replace the commonly known prior or reference probability P by a commonly accepted partial order. And the partial order is easier, let's say, to be common among all people than a common view of the probabilities. On probabilities, we can disagree a lot, actually. But on the ordering, at least in terms of money, one should be able to find some kind of weak order that what we can agree on. For example, the pointwise order. If I guess that getting more money doesn't hurt. As I like to say, if it hurts you, you can give it to me, and then it's gone. Also, it doesn't. It's not so difficult. We want to talk about viability and absence of arbitrage. I will explain this and what is maybe interesting in the spirit of all these expectations hypothesis and the things that we have seen before, also in Francesca's talk, the fundamental theorem of asset pricing in this setting. There's a large literature, and I haven't even updated it, so it's not up to date probably. But since I thought we were in Oxford, but now I realize we are in London, maybe, no? Anyway, and I would have loved to be in Oxford because my nephew, who's not studying economics, but he's currently studying in Oxford. So it would have been so lovely to be in Oxford, and I hope that it will happen again. But okay, I'm happy still that I'm able to do this online. So let me mention 2 people from Oxford who have contributed now, Obloy, of course, and Sam here, who was one of the organizers here, and there's much more work going on. In the interest of time, I don't spend too much time on that. Let me explain our contribution here. So as I said, due to untitled uncertainty, we don't want to fix any piece. Yeah? So all that we fix is this common ordering. And what is an ordering? Well, so the idea is that it's some kind of weak partial idea of greater equal. For example, you can take the pointwise ordering, but you can also take orderings based on probabilities, like the P almost sure ordering, if you want that, or any other ordering that you might like. So we are very general here, so we just assume that H, that's a possible space of consumption plans, let's say, is a pre-ordered topological vector space. Then we have to define what is negligible, but this is known, of course, in particular to the people in decision theory, who deal with these things a lot. We don't have a measure here, but we have an ordering, so we can say payoff is null if it's at the same time lesser equal and greater equal 0, so equivalent to 0 somehow. The financial market is modeled also in an abstract way here, so we just take some cone of things that you can get for 0. So in the finance setting, this would typically correspond to some stochastic interval of this form here. In Harris and Creps, they also have sort of an abstract form. Now then the market is given by some continuous linear functional, and our convex cone will actually be a subspace now given by the kernel of the price system. Now the agents, so I said that they commonly accept the order. How does it translate into their preferences? Well, the preferences are monotone with respect to that ordering. So that's what we mean really by this commonly accepted order. And then the other conditions that we assume for preferences are standard in economics, convex and sort of semi-continuous. So a little bit, you need some continuity, otherwise you get into trouble. But then with equilibrium, but it's not. This is just a technical condition. So how do we define equilibrium? It's an equilibrium in a market. First of all, I need to define here what I mean by a relevant payoff. But for today's talk, I just take positive. Yeah? So if you see relevant, in the paper we are much more general, but if you see relevant today, I mean positive, so non-negative and not null. And then we say a financial market, which is given by all these ingredients, yeah, age, topology, the orderings, financial traded assets for 0, I, and the relevant things, so the positive things. Such a market is viable if you can find a family of agents indexed by this small a, such that no agent wants to trade. So we have we're considering net trades here. We have corrected for endowments already. So 0 is optimal for each agent. But then this would be sort of trivial to satisfy. You can just take agents who don't care about anything anymore in this world. No, they've been in a COVID lockdown for so long that they are indifferent to everything. So in order to exclude this trivial case, we have to assume that these agents are not trivial. So for every positive payoff, there's at least one agent who prefers this positive payoff to 0. Some sort of quantificity requirement. Otherwise, it would be, this notion of viability would be empty. And we want to relate this condition of equilibrium to arbitrage. Well, let's fix here, and the experts will understand anyway, let's fix this simple idea of arbitrage. So a payoff L star, yeah, so a trade is an arbitrage. Note that these are the trades that you can get for 0, so it's an arbitrage. If I can find a positive payoff, which is below it, so L dominates the positive payoff in terms of this ordering that everybody accepts. That's not the pointwise ordering, yeah? So it's just the commonly accepted ordering here. Let me stress this. And then, of course, as you know, it's important to generalize to free lunch with vanishing risk for some technical reasons. In the paper, we also show under what conditions these two things are equivalent. Discrete time pipe, for example. So then the first main theorem that works here also. Then it was really, the importance is to find the right setup in order to get the classic theorem. So this is the classic Harrison-Creps theorem that says that the whole theory of finance based on absence of arbitrage has solid foundations in the sense that it is consistent with an equilibrium in financial markets. And that's what we get here as well. Interestingly, yeah, so the proof is sort of based not on linear preferences as in Harrison-Creps, but we do it with sublinear preferences, with families actually of linear preferences that then form a sublinear preference, of course. More interestingly, maybe because here for what we have seen this afternoon is the fact that night in uncertainty leads immediately to sublinear martingale expectations, in particular to sublinearity, what we have seen a lot now in this afternoon in Chige's talk and Francesca's talk and so on. So a functional is called a sublinear expectation in this setting if it's monotone. Note again here with respect to our partial ordering, cache additive and sublinear. In particular, it's also convex. So these are the E's that you, as I have also seen arising in Chige's talk. And then, in order to relate it to finance, you know that typically in finance we have equivalent martingale measures. Now there's nothing to be equivalent to somehow here, but nevertheless we use a little bit the language of probability theory. So we call E absolutely continuous if it vanishes for every null payoffs. And null means that is equivalent to 0. We say that it has full support if every positive payoff has positive expectations, strictly positive. That will replace so part of the equivalent. And martingale property, that's a typical martingale equation. Here everything is very abstract because all this sort of these stochastic integrals are here just an L, yeah, so it just would mean expectation of L is equal to 0. As we are quite general, we allow for no short selling and such things also, yeah, so we are sometimes happy just with the super martingale property, but if you think of a frictionless market, then this would really be the martingale property if you can short sell things as well. And then we get the following version of the fundamental theorem of asset pricing. A financial market is viable, which you know is equivalent to no arbitrage, if and only if there exists a suitably continuous sublinear martingale expectation with full support. So full support replaces the old equivalent. And of course, in a sense, it might be clear to some people, but it's interesting that it arises from Knight uncertainty alone. Yeah, this sublinear replaces linear, because in some sense, in the classic case, of course, you have just an expectation with respect to a martingale. As in my previous look at insurance markets, so here again we encounter sort of risk measures or sublinear expectations. And again, as in the previous consideration, this is related with the idea of super hedging, which makes a lot of sense under uncertainty. So, just to give a short look at the proof, what it does is essentially you define super hedging functional and you look at the duality and then you work from there and you get a fundamental theorem. But this is just a remark, let's say mainly, I would say for the experts here today. Let us have a look at some orderings that might be interesting. For example, in economics, the smooth model, as it's called, smooth ambiguity aversion, is very popular. It has been introduced by Klibanov, Marinacci, and Mukherjee. So actually, in the smooth model, maybe I should say, is the utility function looks like this. So if you know the probability, you would have expected utility, but then you don't know the p. Huh? So what can you do? You take a second order prior, mu. And this would be the Bayesian approach, if I leave it like that. So you have a prior over priors. Now you can integrate over a set of priors, but now you're ambiguity averse, so you have another index, ambiguity index, it's called, that distorts this expected utility. And so this phi here measures ambiguity aversion or attitude. And this here is risk aversion, as usual, this U. So such a model is very nice, and also philosophically, because it's still close to the typical Bayesian setup of economics. And we can use such a model in order to define an ordering. So you can say, sorry, this is a typo, it should be lesser equal, really, this partial ordering. We can say, so like this. For example, x is less or equal to y. If p almost surely x is less or equal to y, mu almost every model. So this would be second order Bayesian approach, sort of, but you can derive it from the smooth model as well under Knight uncertainty. And then the sort of martingale measures that you get, so you would get linear martingale measures here, take the following form. Well, they correspond sort of to average martingale measures. So you have a state price density D, which does not depend on P. So really you get a state price as in typical finance models. And then the D and the P, of course, determine a martingale measure, and then you take the average of these martingale measures. In general, for example, you can take a robust approach, based on multiple priors. So that would be in economic terms based on a Gilboa-Schmeidler approach to uncertainty. And then we can, but also in the spirit of robust finance, we can consider the quasi-sure ordering given by a set of priors, set of probability measures on our measurable space. And what is important, that I think she mentioned this, that under Knight uncertainty you have martingales, and then you have martingales where also minus the thing is also a martingale. These are called symmetric martingales, which is of course not an issue in the linear case, but here it is important to distinguish martingales from symmetric martingales. And then the maximal sublinear martingale expectation is generated by those probability measures which are equivalent in a certain sense to M, such that the traded contracts or the traded assets are symmetric martingales. So this was a short glimpse of what happens under Knightian uncertainty in financial markets. And the important conclusion is really that Knightian uncertainty is a generator of sublinearity. So prices become sublinear due to Knightian uncertainty. Of course, they can be sublinear for other reasons as well, but prices can be sublinear due to Knightian uncertainty. That's what we learn here. And that in turn can lead to, well, something that you can call market breakdown. And I would like to explain that. And it is related to another paper of mine with Patrick Beisner, which has appeared in 2019 in Econometrica. So in that paper, we consider markets with sublinear prices, taking Knightian uncertainty as a motivation. Of course, mathematically, it covers other cases as well. No? Sublinear prices have appeared before in economics, of course. We introduce a corresponding equilibrium concept that we call Knight-Walras equilibrium. It would sort of correspond to what we have seen in the previous paper. Then the equilibria are different. That's the first thing. So we don't get the nice welfare theorems that we are used to see in perfect markets. And then we can sort of get some sort of breakdown on the no trade. And I would like to start with that maybe. So with the picture now, let me do this. For those of you who know general equilibrium theory, coming back to Frank Knight, you know Edgeworth box. So let us assume that we have two states of the world. So a very simple model. So state 2, maybe that's consumption in state 2, how much I get in state 2 and state 1. So if you just have a point here, then this would be how much I consume in state 1, and this is here how much I consume in state 2. So a point corresponds to a consumption plan. So now let's look at a very simple economy, so-called square economy, no aggregate uncertainty, where there's another agent. And the aggregate endowment is here. As you no aggregate uncertainty, because the aggregate endowment is such that the society as a whole has no risk, because in state 1 and state 2, we always get 10, let's say, if this is 10. But the individual has uncertainty, this would be the endowment. Now, what would happen under expected utility? We would find efficient allocations, and allocations that are efficient here in this context are full insurance. So a nice economic institution insures everybody perfectly in the situation, because in the aggregate there is no uncertainty. So I can give no uncertainty to everybody if I want to, and markets can do that. I can also do it by other means. So if there's just expected utility, then this would be the price line. And the slope would be given by the ratio of probabilities. And this would be here the equilibrium allocation. Okay, so far so good. You know? So that's a famous theorem in economics. In different curves, by the way, you know, but like this here. You can even go to ambiguity, to Knightian uncertainty, so to allow for Knightian uncertainty in preferences, but even then you would get this result if markets are perfect in the sense that prices are linear. But now let's do the same exercise again when
Frank, apologies. I mean, we are running slightly out of time, maybe 5 more minutes.
Oh, I was too slow. Yeah. Okay. No, don't worry. I show you immediately the picture. I got carried away. I apologize. I was happy with my picture here. I go immediately to the case that, because it's the case that I want to make. Here, market breakdown. You see, in the case of Knightian uncertainty in prices, you have suddenly the budget set becomes convex like this, yeah, given by two, in this very simple case, by two lines. And then it's impossible here to trade to this nice place where everybody is fully insured. And in fact, in this very simple economy, you get no trade at all. And in the paper, we show that this is a generic phenomenon, yeah, so it's not just related to this very, very simple example. But whenever you go away, yeah, if you parameterize Knightian uncertainty, you start with no Knightian uncertainty, and then you blow up a little bit the thing, then the Knight-Walras equilibrium correspondence is discontinuous. So a tiny amount of Knightian uncertainty has a discontinuous effect on allocations. It does not mean always no trade, no, that's not true. But at least the effect can be harsh, let's say. And okay, I would like to conclude a little bit. If you give me a minute, yeah, then this is my last slide. First of all, I have decided that Frank Knight is a mathematical economist. Okay, so I'm not sure if the literature will follow me, but reading him again, I thought he argues like a mathematical economist, and he inspired us. So he's now one of us. Okay, and you've seen a little bit in my talk that his intuition that insurance becomes impossible and market outcomes are inefficient is correct. And this leads, of course, now to interesting questions for future research also, because now we have to deal with the question what to do about Knightian uncertainty. Well, the answer of Frank Knight, I think in the Chicago or Austrian spirit, maybe a little bit, yeah, would be to trust entrepreneurs, to trust freedom, and to trust creativity, which is not the worst thing, particularly if I just look how our governments here in Europe deal with the COVID-19 crisis. Maybe it would have been better to ask some entrepreneurs to do the vaccination. Huh? So that's the answer that Frank Knight gave, coming back to self-confidence and combination with the power to make guarantees. But of course, it also leads to another question that is interesting for theory, namely, can one develop a theory like market design under Knightian uncertainty? And I think I leave it with that question simply. Thank you.
Thank you, Frank, very much for very nice talk, touching on many, many areas, actually. So let's see if we have any questions. Feel free to, so there is, Fabio, I'm promoting you to panelists. If you could turn on your mic and maybe ask yourself the question.
Yes, sorry. So it was just a curiosity. First, great talk. Second, can you just go back to the two definitions of risk measure and deviation measure? Just because I got carried out in the presentation and I was rethinking about them. Actually, they distracted me a lot.
Yeah. Sorry, I do it in this ugly way, but it will come. Because the hyperlinks currently don't work, so it will come in a second.
Yes.
This, no, wait a second. Definition of risk measure.
Okay, sorry. Okay, deviation measure.
Yeah.
Okay. No. It was just that you were a bit fast on that, so I imagine that those were the definitions. Don't you assume some form of symmetry on the deviation?
No.
I would think it's natural because I mean.
Yeah. Okay. Yes. Yes, but we no. So here we don't do it. No. For example, we would also like to allow for asymmetric measures where you just look at the so one direction sort of and measure the deviation of really the losses. Yeah.
Yes. I understand what you mean. You say I might wanna care only about the losses in. Okay. And could you characterize the case where the deviation measure is symmetric?
No, that's a good point. I don't know, actually. We will think about it.
But you thought about it. I mean, for me, it were just things popping in my head while you were talking.
Okay. So symmetry. How would you so if I go from x to minus x, you say, I want to have the same deviation. Huh?
In a sense, yes.
Yes. No, I don't know the answer, but it's a good point.
Okay, Frank, thank you. It was a great talk.
Thank you, Fabio.
Fabio, thank you for the question. Adam, do you want to turn on your mic and maybe ask?
Hello, Frank. It was an excellent talk. It's very informative. I have two questions. So the one question is related to the non-existence. By non-existence, you mean that you cannot find prices and allocations such that market clears, the classical definition, on in which sense you don't have trade. So I missed that point. This is the first question. And second question is, do you have any sense of, so for use in your setup, as I understood it, it's basically one-shot market, right? So basically we determine the allocations and we check if we trade, etc. Do you have any sense if we endow your economy with some overlapping generation models, so will Knightian uncertainty survive in the market in the long run? So those are the two questions that I would have. And besides that,
okay, yes. Let me see if I find the page. The first question was related not to, I think you don't mean non-existent. So there exists an equilibrium here, but the equilibrium has no trade. Yeah, so it's not
so meaning no trade, meaning that they stick to the endowment allocations, right? So there's.
So they. And the reason being that you see that these two here in this very simple setting, these two budget sets, no, they are too different somehow, no, in order to allow any trade that is reasonable for both of them. No? So you get no trade due to this sublinearity. Actually, if you look at this page picture, I think Frank Knight was aware of it already, because this is what you get when you need to trade in two currencies also. So if you have to pay in the future in dollars and in Bitcoin, then you get the same trouble actually. Yeah.
Understood.
It's like having two budget constraints actually, but Knightian uncertainty is a little bit similar to that. And the second question was related to learning, right?
Yes. So basically, suppose that I do this task that at each you have overlapping generations, so there are some new generations. So do you have any sense how the story would unfold, and if Knightian uncertainty, or let's say is trade that is driven by ambiguity, if this preserves over time in the long run, or maybe the non-Bayesians, they will be, I don't know, some diversified out or something like that. Okay.
Yeah, I'm not aware of a general treatment of that. Also, learning under Knightian uncertainty is not an easy subject, as you might know, and this is something also that will come, I guess, in the future. So the thing is, if you have sort of an IID version, so also Shigi was talking about IID of Knightian uncertainty, then you can do this dynamically and it stays the same. But of course, when there's real learning, so there's some parameter that you can learn in the sense that you're in world 3. Yeah, what I said, you reduce uncertainty to risk. Then indeed, if they really learn, would be my conjecture, but I think it's true, then you would converge to the very nice Arrow-de-Broglie equilibrium allocation. But I'm not aware of really a paper that does this. Yeah. So, as far as I know.
Thank you.
Okay, Adam, thank you for the question. And I believe Jan also wanted to ask a question. Jan?
Thanks, Igor. Thanks, Frank. Really nice talk. Can you elaborate a little bit on this discontinuity when you go, as you said, I think from epsilon 0 to non-zero? So first, is this when you go from a single measure to some sort of neighborhood, is that a very generic statement, or do you take this neighborhood in some specific sense of a ball in this place of measures? Is this for your simple, market that was on the next plot, or is it just very generic statement? And is it the prices which are discontinuous, or what is it that is discontinuous? Thanks.
Yeah, so first of all, we do here a very dramatic, in that sense, I agree. Yeah, so you can argue when you go from no Knightian uncertainty to Knightian uncertainty, here we do it in a sense in a dramatic way, because we take some sort of, as it's sometimes called, epsilon contamination. So really it's like a ball. Yeah? Mm-hmm. So that would be a sort of ambiguity in every direction. No? Mm-hmm. You could imagine the case that some probabilities are actually known, like in an Ellsberg experiment. And then this is, so in that sense, this is a strong assumption. I agree with you. But if you're willing to make this assumption that there's something like epsilon contamination, then you get the discontinuity, and it comes, well, in the proof, at some point it boils down to a question of dimensions, yeah, in a finite dimensional setting. Namely, at some point in equilibrium, actually you are forced to find a trade that in finance terms has a unique price for both of you. Yeah? So the ambiguity has to disappear. So in that sense, you have to be in the subspace where of ambiguity-free options, and that's and of course due to our assumption, this subspace has a smaller dimension, and this loss in dimension creates the discontinuity.
Okay, thank you.
All right, I believe there are no more questions, and oh, there is one more. Let's see who's okay. Bernd. So I promoted to the panelist. Bernd, if you can turn on the mic and ask the question.
Can you hear me?
Yes, we can.
Yeah. Okay. I wonder, is there a link with the modeling of bid and ask prices in your framework? Because it sometimes seems that Knightian uncertainty can also be an explanatory factor behind that, but it seems not to be present in your model, in your presentation.
No, it was not present in the presentation due to time constraints. In the paper with Patrick Beisner, we have a long appendix where we show that there's a relation between so transaction cost economies lead to similar structures, no? And actually this is covered by our setup as well.
Yeah, okay, but bid-ask spreads need not be a result of transaction costs. It can also be the result of Knightian uncertainty, I would say.
Yes, no, I agree with you. And that's also one motivation for our paper, in the sense that we think, okay, but this is a little bit, we think of a market maker, no, who runs several models, for example, and then wants to say, if such a market maker wants to stay on the safe side, he creates bid-ask spreads. No?
Okay. It's not it's an additional thing to your model to extend it to bid-ask spread. Okay, so and the price you find in your model, or the thing you model, what is it? Is it somewhere between both, or you simply focus on a market where there is no bid-ask spread, or how should I interpret it?
Yeah, so in general here, what you get is like always, I think, you would get an interval of prices, but sort of the agent, when he considers his budget set, he has to pay the upper price. No? So this is sort of the super hedging price in spirit.
Yeah. Okay. Okay, I will have a closer look. Yeah, but thank you very much for this presentation.
My iPad keeps going away. Sorry for that, but I think this might be okay.
Was it one more? Somebody else wanted to ask another question? I noticed the hand raised, but if not, we are slightly over time, but still it's okay, I believe. So, well, it looks like there are no more questions. I had a question, but I can postpone for a later time. It would be probably good if, I don't know, I at least get hold of the slides, Frank, but I believe others have been also asking if we can share the slides and also the videos. Tentatively to answer, I mean, we received many questions about the videos. Yes, tentatively, we plan to release the videos somehow once our great speakers agree to sign the release form that they are fine with that. And then we'll post them somewhere. That said, I think we should now conclude the session for today.